Hello, welcome everyone, welcome back. So we're gonna continue. Hello, welcome back. So we're gonna continue where we left off. So that means we're gonna continue our derivation. All right. So the last time we left off, we kind of did the right hand side kind of derivatives. Okay. Now that we Now that we have converted the right hand sides into partial derivatives, we then need to take a look at this left hand side. The left hand side, okay, let's deal with it term by term. Left hand side. Alright, so you see this tau x over here? Tau x over here has like nothing to do, even nothing to do with delta x. So that even if you take a limit the delta x goes to 0, it will still be the same. I think my limits should be different. It should not be x equals to 0, it's delta x equals to 0. Alright, kudos to you. If you you found that mistake, kudos to you. Let's see, where am I supposed to paste it? There you go, the limit. Yeah, kudos to you if you actually managed to find that out. And got very sharp eyes. Okay, so tau x doesn't have anything to do with delta x, so we can just take it out very easily. Now, a question is, you probably have to start dealing with all these terms over here, and that's a little bit more troubling because they don't look exactly like derivatives. Okay, so we'll need to do something to convert this into sort of a derivative form. And remember what's the derivative form? Okay, we go and look at GIM. Okay, I'm going to start. Okay, derivative form. It's like this, right? So you have y2 minus y1 over delta x. Okay, and you limit delta x. Okay, limit delta x goes to 0, right? Of this whole thing. And this delta should be a complete triangle, not a volcano-like looking shape. So you have to have a y2 that's evaluated at x plus delta x, y1 that's evaluated at x, right? So maybe we call it x2, and then this one is x1, and delta x of course equals to x2 minus x1. So that's how this is supposed to look. Well, y can be any variable, and in this case we look and y looks like p delta p. Okay, p delta p, which is the pressure multiplied by the momentum layer thickness, momentum boundary layer thickness. However, there's no subtraction sign here. And over here there's no subtraction sign, so we need to introduce in subtraction sign. Okay, so what's the easiest way? Okay, if you look at the right hand side term, okay, this one looks a little bit like the first term, right? This is evaluated at x plus delta x, and it should be a minus p of x. So let's introduce the minus p of x there. Okay, so I'm just going to only deal with terms inside this limit. And this term is supposed to look in the terms inside the limit. And how much time do I have left? Okay, so let me start a timer. Don't want to go too long. Okay, there you go. Okay, maybe about 15 more minutes, and I'll stop. Okay, so this one should be a minus p of x. So let's try introducing a minus p of x in there, just to make it a little more easy. Okay, so minus p of x. And to introduce a minus p of x, I need to plus a p of x somewhere else. So I'll just put the 2 in front. Okay, so this should be what it looks like. 2p of x minus p of x, and this one looks a little bit more like a derivative. Now mind you, there is still this term over here which we'll need to deal with, but we'll talk about that later. Let's bring this p of x out first. Okay, let's bring this p of x out, and yeah, we'll bring this p of x out, and that will be multiplied by half, and of course whatever this thing is here. Okay, copy and paste. So whatever this thing here, it needs to be multiplied in. Alright, so this p of x here, we'll deal with this part later. Okay, and of course this whole thing is divided by delta x, because there's a delta x at the bottom, so I'll need to include a fraction. Okay, so let me put some equal signs in there first, because this is a very long equation derivation. Okay, so this thing already you can see it's just p of x, is pressure at x, and then this thing becomes a derivative. Okay, delta p by delta x, delta p by delta x, if you know what I mean, the partial derivative of this momentum boundary layer with respect to x. So this is a partial derivative. Let's just take that out. Okay, so let's take out this partial derivative term. So p of x, and that will actually save us some space. P of x, fraction partial, okay, delta p, partial x. And the last term we can just get rid of. Oh, okay, I think I deleted too many things off, as usual. Okay. So this thing we take out, and the residual terms in here we will kind of have to multiply out. And I'll just take out the p of x. I just put the pressure just for simplification. I mean, pressure evaluated at x is just pressure. We kind of imply that it's evaluated at x. Okay. Oh shucks, I really deleted too much there. Okay, let's see. I still have minus delta p of x on the right hand side. Okay, so now we'll need to get a little bit messy. So I think this part can also be brought out. Okay, this part can also be brought out. But first thing first, I think we can actually multiply the products in. Okay, let's multiply this delta px plus delta x into all of these terms here, and of course minus delta p of x as well. So alright, it's a little long-winded, I admit, but that's what we gotta do. So let's put this here. Okay, I'll put a minus half on the second one, and let's paste this one here and this one here. Okay, I'll delete that. Now I'll delete this. Alright. Okay, now hope you can see what's going on. We have this t delta x, okay, and okay, maybe I don't do it like that. All right, I'll just it's a bit hard to see. Let's do this. We'll just do it this way. Alright, you can see both of these terms here, they are like partial derivatives sort of a thing. However, there's still this delta p evaluated at x, delta p evaluated at x plus delta x. So some of these terms will actually cancel with some of these terms here. So let's see what happens. Okay. Yeah, so to see which terms cancel out, it's probably still better to multiply those terms in and then see what happens before we apply limits. Okay. So let's just multiply the terms in. Looks like there is no other way to do that. We cannot just take out the excuse me. We cannot just take out the limits like that. So we'll have to do it the harder way. That's life. That is life, my friend. Okay. Okay, so let's see if there's any luck with any luck now, with any good fortune or what. I mean, if things go our way, we should be able to start cancelling terms. Now you notice this term here, delta p evaluated at x plus delta x, and the p evaluated at x plus delta x. That is simply just this term here. So I can just put these two together in a bracket. Okay, so and let's see what other terms can do the same as well. So this is one term that looks very neat. Okay, what's the other term? Is this one here. This one over here. Alright. This little fella over here. We can also do the same thing. So let's just do the same thing for the sake of neatness. So let's have everything of this evaluated at x. Yeah, we are of course hoping terms can cancel, but they are not quite cancelling yet, as you can see here. They are not cancelling. Okay, these terms and these terms look similar, but they won't cancel out. Okay, now we have this. Let's try bringing all these terms over, and then we'll see what happens. Okay, so we'll have to bring this delta p, this whole thing here, evaluated at x plus delta x to here. So that will just be 1.5 p delta p evaluated at x plus delta x. So let's just do it very slowly. We don't make any careless mistakes. .5. So that enables us to just delete this term off. And what's this term here? We can do a subtraction for this term. We can do a subtraction for this term. So this one will be subtracted from this to get you 0.5. Okay, let's do a 0.5, and then we'll just take off the last term here. Oh wait, it does not look like a 0.5, does it? There's a minus and a minus. Yeah, there's a minus and a minus here. So it will be a 1.5 as well. Sorry, 1.5. Okay, so let's get rid of this. So the a minus times a minus becomes a plus. It's always a confusing bit. And this fella here, we'll just take it down. Okay. Of course, this 1.5 should be inside the fraction thing. Okay. Okay. What else can we do? We see that this term here becomes essentially a derivative. So at least for the sake of space, we might be able to take it out. Yeah, we might. I'm not saying we can, but we might want to try. Yeah, so to take it out, we need to do the same trick again. You have to do a minus p delta p. All right, so that that we can bring this derivative out. So let's do this. Let's do it this way. 3 p delta p evaluated at x. Okay, so now we can bring this derivative out, and then it will become straight away for us a partial derivative, as you can see here. Okay, I'll just bracket it up properly. Okay, let's see. Yeah, this one will become a partial derivative of what? Okay, p. Yeah, it's just the full derivative. Partial of p delta p. All right, partial of p delta p. So let's bring that out. Let's bring that out. Minus fraction partial of p delta p partial of x, and this whole thing is actually 1.5 times, right? 1.5. So yeah, now that should about do it. Okay, so this should be a plus 1.5 plus, and that's the rest of the terms in there. Okay, it doesn't look like we can really combine so many terms anymore. Okay, but the thing is we can. We can actually. You know why? Because when we shift this over, this becomes a partial derivative. Shift this over, this becomes another partial derivative. If you know what I mean. Yes. Okay. Let's see. Yeah, so let's bring as many partial derivatives as we can out. And then let's see what we have left. Okay, partial derivatives here. Now let me show you what I mean, and then maybe we'll continue in the next video. Okay, so this actually can be brought out here. So we can take half out to complement this one. Okay. So let's see, let me show you what I mean. I'll take half out. Okay, I hope you got all that. I hope I didn't pause the video by accident. But this is basically what we are getting. We are getting this term out to become this term out to become this. Okay, I'll stop for now. I'll continue more in the next video. Bye.